Good afternoon, and welcome to hand-wavy chemistry. Molecules form when two or more atoms come together and bond. And in this video, we will be discussing covalent and ionic bonding. There is also metallic bonding, but I covered that in my previous video on why metals conduct electricity. Now, in order to understand bonding, we first need to think about why it is that two atoms would want to come together anyway. And we can do that by considering the potential energy for two hydrogen atoms at different distances. As the two hydrogen atoms approach one another, their electrons begin to interact with the nucleus of the other atom. And as they do so, we descend down into a potential energy well. We go to a more stable state. And there is a certain distance at which the energy is at a minimum. And this is what will be our average bond length. If we try to bring the atoms closer together than this distance, we start to increase in energy as the nuclei begin to interact and repel one another. And if you were to push really, really hard and climb up that steep potential energy curve, you could get those nuclei to fuse, like what happens in the sun. But in a normal lab environment, you're not going to have enough energy to get the nuclei together. So from this simple diagram, we can understand that atoms come together and form bonds to go into a lower energy state. And if we wanted to break those bonds and get the atoms apart, we would have to put energy in. Now, I mentioned at the start of the video that there are two types of bonding we're going to discuss today, covalent and ionic. Let's start with covalent. In a covalent bond, the atoms share electrons, and each covalent bond is two shared electrons. So when you see a diagram of a chemical molecule and you see a single line representing a bond, keep in mind that that is two electrons being shared by the atoms. At this point, it's natural to start to wonder about how many bonds an atom would want to form. And experimentally, we can see that when atoms form molecules, they try to achieve the same number of valence electrons as a noble gas. So we often call this the octet rule. So if you think about the second row of the periodic table, there is one 2s orbital and three 2p orbitals. And those four orbitals can each hold two electrons for a total of 8 electrons, hence the octet rule, trying to get 8 valence electrons around an atom. For a lot of transition metals, you'll hear chemists talk about the 18 electron rule, and we can rationalize it in a similar way. 1 s orbital, 3 p orbitals, and 5 d orbitals. 1 plus 3 plus 5 is 9 orbitals there. Each one holding 2 is a total of 18 electrons. So in order to reach the right number of electrons, atoms may actually need to form more than one bond. For example, oxygen. Oxygen starts out with 6 valence electrons. If we bring two oxygen atoms together and they each put in 1 electron to the bond, and now we would count around, would say there's 1, 2, 3, 4, 5, 6, 7. We're still an electron short. So if we make a second bond, now when we do our count, we have 1, 2, 3, 4, 5, 6, 7, 8. And for the other oxygen, also 8. Note that I counted the electrons in the bond twice. I gave them to each oxygen atom because they are being shared. But electrons are not always shared equally. When we brought those two hydrogen atoms together, I talked about the electrons being attracted to the nucleus. But unfortunately, not all nuclei are created equal. Some of them are much better at pulling electrons to them than others. For example, fluorine. Fluorine is the most electronegative element. It is the best atom at pulling electrons towards it. If we think about a carbon atom sharing electrons with a fluorine atom, the carbon atom has 6 protons in its nucleus. The fluorine atom has 9. So that electron is going to be pulled towards those 9 protons in preference to the 6 on the carbon. And we see this as a general trend across the periodic table. As we move from left to right across the periodic table, electronegativity increases. The atom's ability to pull electrons to it goes up. There is an exception, which is those noble gases on the end. They already have a full octet, and so aren't really interested in bonding, and as such aren't really trying to pull electrons towards them. Now you may think, okay, if just having more protons makes you more electronegative, jumping all the way down towards the bottom right corner of the periodic table should actually be the most electronegative, not fluorine, which is in the top right corner. Well, there are 2 things that influence how attracted an electron is to the nucleus. One of them is how many protons are in the middle, and the second is how well that electron can see the charge. As we go down the rows of the periodic table, our atoms get bigger and bigger, so our valence electrons get further and further away from the nucleus. We also have full shells of electrons, like layers of an onion, blocking the nucleus from that electron. And so, although there are more protons in the nucleus as we go down a row, that increased distance and the increased shielding mean that the electrons don't see it as strongly. Now let's continue thinking about an electron being unequally shared, and try to take it to the absolute extreme, where it's no longer really shared at all, but instead transferred from the less electronegative atom to the more electronegative atom. At this point, we have an ionic bond. And this is not just some kind of academic bookkeeping. If we take a material like sodium chloride, table salt, and we dissolve it in water, we see the atoms come apart, and we have sodium plus and Cl minus. They are stabilized by the surrounding water molecules, which is why sodium chloride doesn't just drift apart into sodium and chlorine atoms while it's sitting in your salt shaker. But the electron has absolutely been transferred from the sodium to the chlorine. Now, why might it want to do this? Remember, I said the atoms are trying to get to the same electron configuration as a noble gas. For chlorine, it just needs 1 electron to move 1 to the right. For sodium, if it were trying to move to the right until it reached a noble gas electron configuration, it would need to pick up 7 more electrons. Alternatively, if it loses an electron, it moves to the left, wraps around, and we're at a noble gas electron configuration. If we were to go to the second column of the periodic table, so something like magnesium, those elements will give up 2 electrons for exactly the same reason that sodium gave up 1. It's going to move 2 spaces to the left, wrapping around to have a noble gas configuration. And ions don't have to just involve single atoms. We can have polyatomic ions. For example, the hydroxide ion. If a water molecule loses a proton, what is left behind is OH minus. And if we were to count up the electrons around it, we would see that the hydrogen formerly has 2 electrons, which gives it the same electron configuration as helium, and oxygen now has 8 valence electrons, giving it the same electron configuration as neon. And our polyatomic ions can get much more complicated than that. For example, there's the sulfate anion, SO4 2-, and the phosphate ion, PO4 3-. And once we start getting into the world of transition metals and inorganic chemistry, we start to have no real limit to how many atoms we could have in a polyatomic ion. But that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.